Hello students, today we will discuss design of two-way slab. In previous class we have studied the design of one-way slab system and now we will study two-way slab system. The difference between one-way slab and two-way slab is in the one-way slab we are going to provide the reinforcements or the, let's say, this steel, HT steel or the strands in one direction, but in two-way slab we are going to provide in both the directions. So this is the design data, that is panel size 6 meter by 5.2 meters. It is a discontinuous edge. Overall edges means it is discontinuous on all the edges and it rests on the beam, and live load is 6 kilonewton per meter square. And materials used concrete grade M40 steel, HT steel, nominal diameter of the strand. This is available in IS code again. 15.2 mm and nominal area of the strand is 139.4 mm square, and breaking load or strength of the strand is 250 kilonewton. Let assume 20% of loss, then eta value will be 0.8. Let's consider type 1 structure. So tensile stresses during transfer and working will be 0, and compressive stresses during working stage and the transfer stage should not be greater than 6 Newton per mm square. So these are the data available, and we start the designs. First we will get what is the ratio, Ly by Lx ratio, that is two-way slab or one-way slab we need to check. So as it is mentioned here, panel size 6 meter by 5.2 meter, it will be two-way slab, because Ly by Lx, if we calculate it manually, it will be 1.15, so which is less than 2. So we can say that this is two-way slab. So by thumb rule, let L by D ratio is 45. So depth is equal to span by 45 will give us 133.33 mm. So this will be the effective depth here. Let's consider the cover as 30 mm. So overall depth of the slab will be 133.33 plus 30 mm. It is 163.33 mm. So giving the here side depth, let's provide overall depth as 175 mm. So when I provide 175 mm overall depth, then effective depth will be, as we have provided 30 mm cover, then effective depth will be 175 minus 30. This will be 145 mm. So now we have thickness of the slab, depth of the slab. Then we can go for the calculation of self weight of the slab. So now we will calculate self weight of the slab, load calculation and bending moments. So starting load calculation, self weight. So density 25 kilonewton per meter cube for 1 meter span we are considering, and thickness is 175 mm, means 0.175 meters. So 25 into 0.175 will give us 4.375 kilonewton per meter square dead weight of the slab. Imposed load is being given 6 kilonewton per meter square, and let's assume floor finish of 0.5 kilonewton per meter square. We can assume 0.5, 0.75, so on. So let's consider here 0.5 kilonewton per meter square floor finish. So overall or the total load will be now 6 plus this 4.375 plus 5. So this yields totally 10.875 kilonewton per meter square. Now we'll calculate design load. Design load is equal to 1.5 times dead load plus live load. So that will be this 10.875 and live load is 6 into 1.5. Okay, live load is 6 and dead load is 4.375 and floor finish is 0.5. So this total comes to 10.875. So 10.875 into 1.5 will give us that design load, that is 16.31 kilonewton per meter square. This 10.875 into 1.5. Then we will calculate the bending moments. Here bending moment will not be calculated as WL square by 8 as the slab is spanning in 2 directions. So we are going to use the IS code 456 2000 coefficients, bending moment coefficients, and we will obtain maximum bending moments. So we have this chart in IS code. This table is available in IS 456 2000 with different conditions, edge conditions. So here it is simply supported on all 4 sides. Here only one side, this side and this side, they are discontinuous. Here it is continuous. That is, 2 adjacent edges are discontinuous here. This is an internal or interior panel where all the edges are continuous. These 2 are discontinuous and this is continuous. Here 3 edges are discontinuous and this is continuous edge here also, but here it is longer span is discontinuous and this is continuous, and this in this case the shorter one is continuous. So similarly there are different conditions here. So here only one edge, that is shorter edge, is discontinuous. Here 2 shorter edges are discontinuous, 2 longer edges are discontinuous, 3 edges are continuous, here all are discontinuous. So such conditions are there, and we have Ly by Lx ratio, and with respect to this Ly by Lx ratio I am going to obtain the value of alpha x and alpha y. So this is with related to the end conditions, edge conditions. And again we have 2 movement coefficients here. One is negative movement coefficient and another is a positive. So the top values are negative and bottom values will be positive movement coefficients. We will be obtaining the coefficient from the above table. So again I am going to show the table here in IS 456. Here is the table which we can refer here for obtaining the coefficients. It is in page number 90. Okay, here it is under the class T, that is annexure 2D 2.1 simply supported slabs, and here spanning in X direction, spanning in Y direction. And this is the table which we are going to refer here, that is bending moment coefficient for rectangular panels supported on 4 sides with provisions for torsion at corners. So we are going to obtain Ly by Lx ratio, and with respect to this Ly by Lx ratio I will be obtaining the value of alpha x and alpha y for different conditions. So here we have different conditions with 4 different cases, and we can obtain negative bending moment and positive bending moment coefficients, and these coefficients will be multiplied to the load into L square, span square, as we did in the one-way slab. In one-way slab, it is W L square by 8. So W is there, L square is there, divided by 8, simply supported case. But here it is spanning in 2 directions, so we are going to obtain moment in 2 different directions with multiplication of these moment coefficients alpha x and alpha y. So we'll calculate, after this we'll calculate bending moments. Mx is equal to alpha x W into L square, that is going to be here 29.98 kilonewton meter. 5.2 is the shorter span which we are going to consider here, that is Lx, and My we are going to calculate with change in alpha y values. So alpha y into W into Lx square it is. So alpha y is 0.056 into 16.31 into 5.2 square. It is 24.69 kilonewton meter. Once we have this, we are going to distribute the moments. So total bending moment in the middle strip, it is shorter span 0.75 into this value mx, and for the longer span again it is 0.75 into the calculated bending moment. So this shorter span moment will be 134.91 and longer span moment will be 96.29 kilonewton meter. Once we calculate this, we are going to calculate eccentricity values of Ex and Ey. So Mx or My is equal to Ex into Px or P, and it is Ey into P. So we need to calculate the value of Ex and Ey, then we are going to obtain the value of force required. So here total thickness provided is 175 mm, and if I divide that into 3 parts, because upper kern and lower kern will be there, and I am going to lay the cables with respect to that. So I will divide this in 3 parts. It is 58.3, 58.3 and 58.3 mm, and now I will calculate the distance between top of the kern and the CG. So 175 is the total of the overall depth, 30 mm minus 58.3 mm. That will give 86.7 mm. Here 175 minus 50 minus 58.3. So the value will be here less than this value, because total depth is 175 minus 30, that is the cover for the shorter direction Ex, and 58.3 is this value. So this 58.3 minus this 58.3 minus this cover will be deducted in the overall depth. And here also overall depth is 175, and here the cover is 50 in the other direction, and 58.3 is the distance from one to the another strip, and it is Ex Ey will be now 86.7 mm. So here next we will calculate the Mx and My. It is P into Ex. So P we need to calculate. We have Mx and Ex. Substituting that, we will obtain the value of Px. So it will be 1556.05 kilonewton. After that, similarly, we are going to calculate My. Again, substituting My and Ey. So Ey will be 66.7. A small correction here it is. It is 86 written here, but it is 66.7. So this will be now Py value will be now 1443.62 kilonewton. So we have required force in 2 directions as Px and Py. Now we need to choose how many number of here we need to choose how many number of strands or the cables are required. We have total Px value as 1556.05 kilonewton. So this divided by 250, that is the strength of a single cable or the stand. 250 is the strength of one cable. So this is the total force and this is the strength of one strand. Then it will give us number of strands. So 1556.05 divided by 250. So this value will give us 6.22. So rounding off that, it will be 7 cables are required in the shorter span, but in the longer span the value of Py is 1443.62, 1443.62 divided by 250. So here we will obtain the value of long span cables. So number of cables required in the long span is 5.7. On rounding off, that will be 6. So now as it is a slab, we are going to calculate the span, this spacing of the cables. 0.75 into 6000 divided by 7. 6000 is the span in the longer direction. So shorter span, it is 0.75 into 6 divided by 7. This is for the shorter span. 0.75 into 6000 by 7 will give us 600 mm spacing, and for the longer span it is Lx. So Lx is 5200. So it is 7.75 into Lx. This 5.2 meters. Here I have written in mm. So it is 0.75 into 5200 divided by 6 will give us 6 point, will give us 650 mm. So we have now spacing for the cables. After the calculation of spacings and number of strands or the cables, we will calculate ultimate flexural strength or the moment of resistance, for which we are going to use IS 1343-2012. In table number 11, for different conditions like post-tensioning and pre-tensioning, we will be obtaining the value of FPV from this value, and we will be obtaining the value of XU from these values. So we need to start calculating this one first, that is APS into FPU divided by B into D into FCK. We have calculated number of cables required, and number of cables into area of one cable will give APS, and B, D are the breadth and width of the beam slab, that is 1 meter by 1 meter here per meter span we are considering, and FCK it is grade of concrete, and FPU. So how to calculate FPU? We have already learned this. FPU is the load divided by cross sectional area of the cable. So breaking load, it will be obtained from the IS code, and it is already stated in the data. Breaking load divided by nominal cross sectional area of one single strand will give us FP. So we'll calculate FPU and remaining things, then substituting the values in this will obtain the value of this term. So here let's say the obtained value is 0.15, then corresponding to this 0.15, what is the value of FPV divided by 0.87 into FPU we need to calculate. So here I will obtain, with respect to this value, I will obtain the value of this term. Let's say we are concentrating here about the post tension slabs. So for 0.15 we will be having the value here for post tensioning slabs 1. So FPV divided by 0.87 into FPU is equal to 1. So I will be calculating the FPV value as it is equal to 1. So I will be, okay, here I will write here. So this will be equal to 1 now. So I can write now FPV is equal to 1 into 0.87 into FPU. FPU we know already, so we can calculate the value of FPV. So FPV is equal to 0.87 FPU in this case because it is 1. So similarly, I will obtain the value of this XU by D. So here XU by D is equal to how much we will obtain for the value of 0.15 value. So corresponding to this, and for the post tensioning we have the value here as 0.316. So I will write here the value 0.316, and I can calculate the value of xu is equal to 0.316 into d. So depth we have already calculated. It is short term and short span depth we need to consider, and after this we will be obtaining for the value of xu. So here we will be calculating two values, one for the shorter span and another for the longer span, and with respect to that we need to calculate the moment capacity or the ultimate flexural strength. So here in this procedure we will be following, or we will be calculating these two times because it is two-way slab and we will be considering two spans and two moments separately. So we need to calculate this value first, and then we are going to compare the value of this moment, resisting moment value, with the calculated moments, that is mx and my. So here are the values which we need. APS for shorter span, it is 975.8. We have depth 135, and for the longer span it is 115. FCK is same, that is material property 40 MPa for the both case, and FPU also same because one single strand breaking force we are considering, breaking load we are considering, and divided by the area of cross sectional area, it will be same for both the cases. So material properties will not be changing here, but the effective depth, and as the number of cables varies, here APS also varies, depth varies, and MUX and MUY are varying. So now we will calculate the value of this term. As I explained, APS into FPU divided by BD into FCK will calculate, and will obtain the value of FPB. So here is the procedure. First we are going to calculate this, it is 0.25. So once we obtain this, so where is the value of 0.25, we can check that. So 0.25 is here, and with respect to that, zero point 0.9 in this case you can observe here it is 0.9. So the value of this term is 0.9, and corresponding value of xu by d for this value 0.25, it is 0.9, and here it is 0.176. It is not clearly visible here, so here it is 0.176, that is xu by d. So once we obtain these values, we are going to calculate what is the value of FPB and XU. So FPB value is 0.87 because it is 0.9 here. So 0.87 into, we have to multiply this 0.9. So it is 0.9 into 0.87 into FPU. So after that I will be obtaining the value of point here. The value of FPB is equal to 1096.2 MPa, and similarly I will calculate the value of XU. So here XU is equal to 0.488. Okay, small mistake here. So here it is 0.488 into D. So the value of XU will be 65.8 mm. So as I said, we need to calculate it for the two different spans. So here are the calculations for MU. I am going to calculate for the shorter span, 135 mm is the depth, and 65.8 mm is the XU value, and APS is 975.8, and we have FPB values here calculated. So substituting these values in the formula of MU, moment, resisting moment or moment capacity, flexural capacity, we will be obtaining here as 114.8 kilonewton meter. And if we compare this with the MUX, so MUX value is 29.98 kilonewton meter, so which is very small here. This value is small as compared to the resisting moment. So we can say that the capacity resisting moment of the slab is more than the design capacity, so hence it is safe. After this we are going to check for the deflection, that is check for the limit state of serviceability. So delta value we are going to calculate, that will be span divided by 250. So span, it is 5.2 meter, that is 5200 divided by 250, it is going to be 20.8 mm. So less than this deflection will be allowable. Then We are going to calculate the similar values for the longer span, which we have considered here in the shorter span. So here we are going to consider longer span. Again, we will calculate the value of FPV and XU for the longer span. So FPV and XU values will be same, but the varying values will be here. They are APS and depth. So these two values will be same as the value of XU by D and FPV values will be same here. So substituting the corresponding values of this 835, 836.4 APS value and D is equal to 115 mm, we will be obtaining MU ultimate resisting flexural resisting capacity, as it is small mistake has been done here. It is 80.1 kilonewton meter. So 80.1 kilonewton meter we have written here. So this is again more than the design capacity, which is 24.69. Hence I can say that slab is safe. Then we'll calculate again the limit state of serviceability in the longer span. So span by 250, it is 5200 divided by 250, again it is 20.8. So up to this we can go for the calculation in the two-way slab as we have did in the one-way slab. And after this we are going to study about the flat slabs. So about the flat slab, brief discussion is been already done. The video already been uploaded. Go through the videos. In the next class we will study about the design of flat slabs. Thank you.